Hello students, today I am going to teach you the asymptotic notations. The asymptotic notations uh, are the expressions that are used to represent the complexity of an algorithm. As we discussed in the last tutorial, there are three types of analysis that we perform on the particular algorithms. For any algorithm, for analyzing an algorithm on the basis of the space and the time it requires, or comparing the algorithms, that which one among these is more efficient, which one is better than the other, we need certain parameter, and we judge the algorithm's performance on basis of three criteria. The first one, the best case. The best case in which we analyze the performance and algorithm for the input for which the algorithm takes less time or space. There are certain situations in which algorithm takes less time and space and it performs most efficiently. In that situation, its performance is better than the other condition. This condition is called the best case of that algorithm. In that situation, it will take the least time and the space. In the worst case in which we analyze the performance of an algorithm for the input for which the algorithm takes long time or space. This is the situation in which the algorithms performs the worst. In this situation, it takes maximum amount of time and maximum amount of space. Uh, while in the average case or in the general case in which we analyze the performance of an algorithm for the input for which the algorithm takes times or space that lies between the best and the worst case. This is not the extreme cases like best and worst case, but it is actually the average case. So averages. So in all these three cases, we use different symbols or notations to measure the complexity or performance of the algorithm. The best case, the worst case, average case. The best case is the case in which the algorithm performs the best and takes the least amount of the time and the space. The worst case in which the algorithm performs poorly and takes maximum amount of time and space. And the average case in which the performance lies between the best case and the average case. For the different notation for these use are the big O notation. The big O notation specifically describes the worst case scenario. The big O notation is the maximum limit of within which the algorithm will give you the result or maximum amount of the time or space that algorithm would take. I am basically talking about the time because nowadays memory has become so cheap. Initially, when the computer were in the initial first or second generation, the memory was very expensive. So at that time, the complexity of the algorithm was measured in terms of space also. But nowadays, memory has become so cheap, and now we basically focus on the time complexity of algorithm when we talk about the complexity of algorithm. And the big O is the upper bound or the maximum time that an algorithm will take to run in whatever the situation, the worst situations. And the omega notation. Omega notation specifically describes the best case scenario. It is the situation in which the algorithm takes the least amount of the time and space and it performs most speedily or fastly. This is represented by the omega, or it's the lower bound. The big O is the upper bound, the omega is the lower bound, or the minimum amount of the time that algorithm require to give you the output or process the data. The third notation, that is the theta notation, this notation represents the average complexity of the algorithms. This lies in between omega, big O and omega. In theta notation, the most of the time, except for the best and the worst case, the theta notation describes the algorithm behavior. It's bound the algorithm in from the both upper bound and the lower bound, and the most of the time algorithm performance lies in terms of theta. Now we shall discuss one by one each of these. The first, starting with the big O notation. Big O notation specifically describes the worst case scenario. It represents the upper bound running time complexity of an algorithm. For example, O1. Here O1 represents the complexity of an algorithm that executes in the same time or space regardless of the input. Here 1 is a constant number. It does not depend upon the size of the input, whether it is n, 2n, 3n, 4n. It will always take a constant amount of time that's equals to On, and it does not depend upon the input. You may you will somebody who is not very uh, exact having object or clear idea about O1, I'm giving you an example. Suppose you are referencing a particular element of the array, whether it is A5, A6, A10. It will take simply a time because with index it takes a constant amount of time. So assessing an array index will take constant amount of time. So the big orientations of O1 represents the complexity of an algorithm, which will grow linearly with the size of the input, because here on means it depends upon the value of n or the input size. With the increasing of size of the input, suppose we are particularly accessing an element. So in array we know that the data is accessed starting from this initial base point. So with the increasing size index, with increasing size of array, the accessing time will increase with the size of the number of input. The O1 example, in the execution time depends on the size of the array. When the size of the array increases, the execution time will also increase in the proportion of the n. And traversing of the array will take O(n) square. When we traverse through the array, it takes the O(n) square. It is the worst case complexity, and it is directly proportional to the square of the size of the input. Many of the sorting algorithms that we shall discuss, like bubble sort and selection sort, are having the complexity of O(n) square. We shall discuss this later, but starting here, so the upper bound of an algorithm is O(n) square. It means the algorithm will take at least n square times to give you the result. If it is O(n), it means it does not depend on the input. Then it will take and give you a fixed amount of time, a constant amount of time for whatever be the size of the input. So big O is the upper bound. It is defined the worst case of the algorithm. Here are some of the big O notation, and there is a relation in between. They are arranged in the ascending order. That O(n), which takes constant time, the O(n) log n, it's greater than O(1), and O(n), O(n) will be greater than O log n, because log n base 2 is log n is smaller than n, and O(n) log n will be greater than O(n). Similarly, it will be less than O(n) square, and that would be less than O(n) cube, and it would be greater than 2 raised to the power n. Somebody get confused between n square and 2 raised to the power n. So 2 raised to the power n would read after a time the n square terms. So this is very important point to remember, that O(n) square, 2 raised to the power n would read the O(n) square, and the O(n) factorial would be the very of high complexity in comparison to the 2 raised to the power n. So when we draw the graph for the corresponding big O notations, we get the following figures. So the upper one, the higher the complexity or the higher the terms, the higher the upper bounds. So we can clearly see that 2 raised to the power n is lying above the 2 raised to O(n) square, and O(n) factorial is lying at the highest, is the highest upper bound. And the next, the omega notation. As we know that omega notation is the lower bound. Omega notation specifically describes the best case scenario. It represents the lower bound running time complexity of an algorithm. So we represent a complexity of an algorithm in omega notation. It means that an algorithm cannot be completed in less time than this. It would at least take the time represented by the omega notation, or it can take more time than that. it is the best case, so an algorithm will take at least that much time or more than that time, but not less than that. So omega notation is the lower bound. This is the best situation for the algorithm, and in other cases the algorithm will take either equal to this time or more than this time. So here the red line represents the actual running time of an algorithm. It is marked in the red color, and there is a line which is dark and is that represent the omega notation. Some people may get confused that in some situations they are intersecting each other. For a limit after a point, after second intersecting point, it is clearly that the actual running time is greater than the time in the graph of defined by the omega notations. So it becomes the lower bound after a point, second intersecting point, and for example n0. So so this is called the best case complexity. The next and the last is the theta notation. This notation describes the both upper bound and the lower bound of an algorithm. So we can say that it defines the exact asymptotic behavior, and it is the most appropriate complexity of an algorithm in terms of the practical situations, in general situation or average situation. In the real case scenario, the algorithm not always run on the best or the worst case. The average running time lies between the best case and the worst case and be represented by the theta notation. So it lies in between the big O and the omega notations, and it's bound the function from both sides, like the show in this diagram. Here the same actual running time that is represented by the red line is bounded by the two lines, upper bound representation by theta and lower by big O. Here it's a mistake. Upper bound represented by the big O and lower bound represented by theta. So the theta notation represents bounds the actual complexity from both sides, from upper bound and lower bound. In this way, the theta notation is the average case complexity. So, in summary, so we can say that for an algorithm, there are three situations: the best case, the worst case, and the average case. For the best case, it takes the least amount of the time and space. The worst case, it takes the maximum amount of time and space. And in average case, the lies between the best case and the worst case. The big O notation is used for the worst case situation. The omega notation is used for the best case, and it's the lower bound. And theta notation lies in between the big O and omega notations. And the point to remember here is that the O(n) square is 2 raised to power n leads the O(n) square, or O(n) factorial leads the 2 raised to the power n. So the big O notations, omega notations, is the lower bound. It is bound the actual running time from the lower side, and the theta notation bound from the both sides. That's all. So thank you.